Okay, so LeetCode 2463 minimum total distance travel. This is Mark Hart on LeetCode. Till the end of this video, we'll know why only greedy solution will break and where dynamic programming comes into the picture. Okay, so let's break down this problem. So we have been given some robots and some factories, and this factory have a capacity. So what this capacity means is how much robots a particular factory can accommodate. For example, this is 2,2. So this particular factory can accommodate 2 robots. So let's call that as an assignment. And the cost of assignment can be calculated as the distance between robot and the factory. So what we need to do is we need to find the minimum distance for all the assignments. Okay, before going to the DB-based solution, consider this thing. You have 2 robots and 2 factories, a robot at point 1 and a robot at point 10, a factory at point 5 and a factory at point 12. So what if we assign this robot at point 1 to the factory at point 12 and this robot at point 10 to the factory at point 5? The assignment cost will be 11, 5 respectively, and the total cost will come as 16. But this is not a correct solution. But consider what if we sort everything. We have the robots array listed as this and we have factories arrays listed as this. Now if we assign this robot at point 1 to the factory at point 5 and the robot at point 10 to the factory at point 12, the cost is coming out to be 4 and 2 and the total cost is coming to be 6. So this 6 is always better than 16. So a sorting technique will help us for getting a better solution. When we sort things accordingly, we will be sure that any robot which is being assigned to any factory, this distance will be the minimum possible. So let's see why greedy feels. Consider we have robots and factory, a robot at point 0, point 5 and point 6, a factory at point 2 having capacity 2, factory at point 6 having capacity 2. Now what greedy says is assign each robot to the nearest. So for 0th robot, the nearest slot will be 2 and the cost will be 2. For the 5th robot, the nearest slot will be 2 and the cost will be 3. And for the 6th robot, the nearest cost will be 6 and the cost will be 0. Now the total cost is coming 5. Consider what if this robot at position 5 skip the factory 2? Then what will happen is it will have to go to the factory 6. So let's calculate the cost in that case. The robot at 0 will have the similar cost which will be 2. The robot at 5 will now be assigned to the factory at 6. So the cost will come to be 1. And the robot at 6 will be assigned to the factory at point 6. So the cost will be 0. The total cost here will come as 3. So we can see 3 is less than 5. Now why a greedy approach will fail is because greedy always works in an isolation. A greedy approach will never know, like if we skip something, there it can find a better solution. Let's go through this technique. So when we are solving a problem for DP, it's better if we solve for a single slot. The factory array which has been given to us contains 2 things, the position and the capacity. But if you see, we can flatten this array to 2 to 5. So what this capacity just stores is tells us is how many robot this factory can handle. So you can just flatten this array into a different array, flattened array, and store the things accordingly. So if we follow this approach, what the problems will convert to is given a robot list and a flattened list and assign each robot to exactly one sort and minimizing the cost. So how this flattened list will help us? So consider this robot and a factory, a flattened factory list. So at any particular point for this robot, we can decide, okay, we need to pick this factory or we need to skip this factory. So we have seen previously, like greedy will not help us. We have to skip things to move forward. So yeah, in this way, this DP technique to flatten things will help us. When making a decision for any robot, we can see if we can pick this factory, this factory, this factory, this factory, and check what factory can give us the minimum solution. So I've just drawn a decision tree. So for f of 0, we can pick so this 0 represents the position of the robot and this 0 represents the position of the factory. So at any index we can choose will this factory work for us or will this factory won't work for us. And similarly this 3 will go down. So this is a simple decision tree which is being made for recursion. So if you see, there are some repeating subproblems. When you have repeating subproblems, what you do is just memorize the things. So why memoization is required is it reduces the time complexity in the pseudocode. The full code will be in the comment section. So what we are being given is the robots array and the factory array. So as discussed, we will first sort the robot array, sort the factory array, then flatten this factory array to a single to a 1D array. Okay, so after that it will look like this. We are creating a DP array as discussed for the memoization. Fill this DP array with -1 to denote that no computation has been done, and then call a helper method with this robot array, this flatten array, the 0 representing the index of the robot array, and the this 0 representing the index of the flattened array, to decide if this robot can be solved by this factory, and just pass your DP array to. So what this helper method will be doing is, so let's first discuss the base cases. What if this I, the representing the index of the robot array, crosses the size of the robots array? So this means that we have explored all the robots and then we just need to return 0. And what if the j has increased? So this j represents the flattened array. What if we have explored all the factories? There are no factories to explore, but we have a robot for which we need to do the exploration. Then what will happen is we just need to return the max. So this is an invalid case, right? So and then we have to find the minimum. So returning max makes sense here. What if the dp I comma j have already done its computation? So no need to compute things again and again. We'll just return a -1. Here the basic case of take and not take. So at a position I comma j for this robot I and this factory j, we can factory will solve for this robot. In that case, we'll compute the cost and then just call the next things using the I+1 and j+1. And if the not take case, we don't need to calculate any cost. We will just keep the robot and move to the next factories. After every computations are done, we'll have the take and not take, and we'll just store the dp minimum of them in the dp of I comma j and return the dp of I comma j at the end. Let's discuss about the time complexity. The time complexity will be order of n cross f. So f is the total number of factories combining the capacities too. The space complexity will be same, order of n cross f. So yeah, if you have solved this problem, you can solve some similar problems. The longest common subsequence, which is the foundation of this pick and not pick technique, and this edit distance problem you can also solve for the take, skip and replace kind of technique. So that's it for this problem. If you are in the same journey of interview preparation, you want the content on LeetCode, LLD, HLD or GenAI, please follow along. The code will be given in the description. Thanks.